My name is Yashan Ho, and I'm head of product for Masterful. Masterful is a low-code platform to train computer vision models. This video is targeted to developers and data scientists who are interested in adding CV to their applications. In this video, I'll talk about what Masterful does, why you'd want to use it, and then I'll give a demo of using Masterful. So let's start with what Masterful does. Concretely, Masterful takes as input images and labels. That's the training data. Masterful trains a deep learning model and then outputs that trained model onto disk. It's outside the scope of Masterful to acquire data or generate labels. But as you'll see, with Masterful, you can get going with a lot fewer labels than traditional ways of training models. It's also outside the scope of Masterful to deploy models into a production environment. That's a task for developers based on their product requirements, like real-time access versus batch processing, latency and throughput requirements, and edge inference versus inference in the cloud. So why use Masterful? First, Masterful is going to be a lot simpler than building a model from scratch using PyTorch or TensorFlow. Those languages are really powerful, but they're also really primitive, so it's going to take you a long time to get a model built. Second is the problem of hyperparameters. Getting them right is critical in deep learning, but getting them right requires either years of experience or dozens of experiments. Masterful handles the selection of hyperparameters. You can think of it as Masterful running all the necessary experiments internally and automatically. Finally, Masterful gets you the best accuracy possible through two basic techniques. First is advanced regularization, and second is semi-supervised learning. Advanced regularization means that Masterful squeezes out all the information possible from your labeled training data. Semi-supervised learning means that Masterful also takes unlabeled data, namely images with no labels, and further increases the accuracy of models using that data. Now that we've talked about what Masterful is and why you'd want to use it, let's go through an example of training a computer vision model with the Masterful platform. In the next couple minutes, we'll define the product we want to build, we'll acquire the data, we'll show how we label that data, then we'll configure Masterful, kick off a training run, visualize the results of that training run, and then actually take that model that the platform outputted and run inference on it. Let's get started. While I set up my development environment, let's define our software we're trying to build through a user story. As an airplane enthusiast, I'd like to scrape social media and identify images of aircraft that I'm interested in. Cool. So the first thing we're going to do is try to gather those images. Great. Let's create ourselves a directory to play around in. And we stored all the files you'll need to run this demo for yourself at this location. Now that we've got this downloaded, let's see what we've got. Looks like a couple of CSV files, a YAML, and the images directory with about 10,000 images. Well, let's fire up Visual Studio Code and take a peek inside those files and directories. So images is 10,000 images that represents the training data. Working through our scenario of building an application to help scan social media for airplanes, one of the first decisions we have to make is what type of airplanes we actually want to classify. The place you define that for the Masterful platform is in the label map. This describes all the classes that we really care about, and we add a 9th class, or actually a 10th class in this case, for all the unidentified types of images. So you can see there's a mix of some military and some passenger aircraft here. Once we have this defined, we actually have now an integer that represents each type of airplane that we're going to classify. And then manually labeling your training data just means looking at each image and assigning it an integer value and then putting it in a CSV file like this with a path for each of the image files and then just a number that represents the class. If you're doing something like object detection, then you're going to want to use a more professional tool like Label Studio or Labelbox. So once we have the images downloaded and these CSVs that represent the labels, we're actually ready to start configuring the Masterful platform. And then once we have it configured, we can kick off training. So let's look at what a configuration file looks like. The key thing to observe here is that there are very few decisions you have to make here. This is the whole point of AutoML. It's taking care of a lot of the stuff behind you. You don't see hyperparameters for batch size or learning rate or augmentation policies. The platform's figuring all that out for you, and that's what's going to save you a lot of time. So now I've told you about what you're not going to see. Let's actually look at what we do have to specify. First thing is just to decide what kind of computer vision task we want. In this case, it's single label classification. Every image represents one type of object. There are other computer vision tasks that Masterful supports, such as having multiple types of classes of objects in an image, which would be multi-label classification. Binary classification, which you can kind of think of as the existence of two possible labels, but normally we think of it more of like as a positive or a negative, like is this item defective or is it not? Is this item a dog or is it not? And then object detection, which means putting bounding boxes around the items you see in an image, and semantic segmentation, where you're drawing outlines and filling out the polygons that represent different instances of objects. Below that, we have a couple of different pointers to label files. So training.csv, validation.csv, unlabeled.csv, and test.csv. Each of these is a CSV file that represents images and labels, except for the case of unlabeled. And let's just take a quick look at unlabeled. The case of unlabeled is just a pile of images because obviously we haven't gone through the effort of labeling them. And this is the heart of, or this is where the rubber hits the road when it comes to semi-supervised learning. Masterful is the only platform that I'm aware of where you can take your unlabeled images and improve your model's accuracy from them. Coming back to the YAML. Next is architecture. The old view was that architecture was a very important decision, so important that ideas like neural architecture search came into play. The data-centric view that Masterful subscribes to is that the quality of your data is the most important factor. The choice of architecture is actually a mechanical one. Either pick an architecture that matches the capabilities of your edge hardware device, or if you're running inference in the cloud, start small so that you can get a model working, then iterate by experimenting with larger models. Larger models will often be more accurate, but they will always be slower and more expensive to run. For cloud inference, go with the smallest member of the EfficientNet v2 family, namely B0. Once you get that model going, you can experiment with larger models, namely B1, B2, B3, etc. The number of classes is actually repetitive with your label map. We just want to make sure that the model that is generated predicts the number of classes that you expect that you've defined in your label map. And finally, the input shape. As a rough rule of thumb, most models are trained on something around 224 or 256, so those are good values to use. But if you have really large images, you may not want to downsize them before training. And so if your natural image size is consistently, say, 512, 512, then you can put 512, 512.3 here, and that'll allow the model to train on native image sizes. And then after that, we're really just specifying a couple of file paths. So where we want to save the model to, what format, namely TensorFlow or Onyx, or both. And finally, a root path that just kind of helps Masterful navigate itself in your file system. Well, that's it. That's all we actually need to specify to get Masterful going. So what I'm going to do next is activate a Conda environment where I've already installed Masterful. And there it is, 052 is installed, and that's the latest version. The first thing Masterful will do is analyze your training data set validation data set, holdout test data set, and unlabeled data set. It's going to print out some summary statistics that you should manually verify, including the label distribution in both absolute numbers as well as on a percentage basis, as well as the image sizes. You want these to be consistent between your training data set, validation data set, holdout data set, and test data set. We can see that for our data sets, the images are about 1100 by 700 pixels, and that Boeing 747s are the dominant class. We also want to look for duplicates. We don't want duplicates within data sets, nor do we want duplicates to exist across data sets. Masterful is ready to start its meta learning now. It's not yet training, but it wants to figure out a lot of those key hyperparameters so that you don't have to deal with them. Let me focus on the optimization parameters of batch size and learning rate. A key to taking advantage of your GPU that you're spending a lot of money on is to have a proper batch size. And then a key to taking advantage of batch size is to have a proper learning rate. And a key to having a proper learning rate is to have a good warm-up schedule. So these are things that you want a platform like Masterful to solve for you. You do not need to go and do these experiments manually. It's the same experiment each time. There's a best practice. It's good to just follow that best practice. The next step is searching for the regularization hyperparameters. And this is going to be a pretty lengthy search. During this phase, there's actually beam search happening where the model is being partially trained and to get signal on what the best hyperparameters are. Now, typically when you search for hyperparameters of a regularization strategy, either you've got to have lots of intuition to kind of manually do your own kind of a search across some values that you kind of bring from your intuition, or you're going to have to do a pretty rigorous grid search, which is what most research does, which is going to be on the order of 2 to 3 or even 4 magnitudes more time, which is obviously impossible. Our algorithm, and we write about this more in our technical report, has its own proprietary method to collapse the search space down into something that's on the order of 1x a full training run. So this is going to go for a while, so we'll go ahead and fast forward from here. All right, the training is now complete. Let's scroll back and see what the logs were telling us. This is where we left off, which is the phase where it's learning hyperparameters for the regularization strategy. It looks like that phase took about 20 minutes to go through. It prints out the parameters, which frankly are not very interpretable. I'll fire up the visualization toolkit in the next section so we can actually visualize what the meta learning algorithm discovered. Now that the hyperparameters have all been discovered, the platform now actually starts the full training step. The first phase is to do a warm-up, which allows us to, again, take advantage of fairly high learning rates and batch sizes. The next phase is a supervised training step, where the model is trained solely on the labeled images. And then the final phase is the semi-supervised phase, where the model is being further improved in accuracy by learning from the unlabeled data. And that whole phase took about 20 minutes as well. The model is now saved into a location on disk. And the platform is now going to evaluate the model on the test data set. Again, the holdout test data set has never been seen during training or meta learning. The platform has never seen it before, so it's true holdout. And it's what allows us to make sure that the statistics that we print for this holdout test data set will accurately reflect what we'll see in production, as long as the data distribution is similar. I resized the screen so that we can see the confusion matrix here. One of the things to note is, of all of the examples of Lockheed L1011s, 30 were classified correctly as L1011s, but about 9 of them were misclassified as DC-10s. This is not totally surprising because both of those airplanes have a third engine in the middle of the tail. So there's not a huge surprise that there's a little bit of confusion there. We print recall and precision on a per class basis. Again, these are statistics that you, the developer, need, and it's your subjective call whether these meet your release criteria. The Masterful GUI will help us visualize a little bit of this, and let's talk about that. Let's fire up Masterful GUI, and then the CLI printed out that we should look for a run that was automatically named make, and so let's look for that one. There we go. You can see that we have reduced the error rate on our model from the baseline down of 6% down to 3.7% by applying Masterful's techniques. The visualization toolkit also includes detail on recall and precision by class. Here, the gray bars represent a model that's trained without Masterful, and the orange bars represent a model that's trained with Masterful. Again, it's your decision to make as a ML engineer or data scientist as to whether this model meets your release criteria. The parallel coordinates plot helps you visualize the regularization policy. Each line represents a different set of hyperparameters that was tested, and the orange line represents the one that generated the lowest validation loss and was therefore selected. And finally, we have some information about the model architecture, which you chose, which was EfficientNet B0. And we also list out a lot of the parameters that we had that were discovered and printed out to the command line. You have them here as well, so you don't have to try to save that command line output. So there we have it. That's Masterful's lightweight visualization toolkit. I've set up a simple notebook that'll take that model from disk and run inference on some images. The notebook has 3 cells. The first cell just sets up some data structures for us. The first is pulling in the label map into a Python dictionary so that we can map numbers to strings. And the second is pulling a couple of rows from the test set, both the file path and the integer corresponding to the class that we believe each airplane belongs to. Secondly, we load that model from disk, and this path was printed from the command line interface. Model output session 000 save model. We take some boilerplate TensorFlow code to index down into the right callable that we can use to actually run inference on a model. And then when we call that callable with an image, we just have to index into the prediction key. And that'll give us the predictions. We take a argmax of that value, and that'll give us the actual integer that corresponds to the prediction from the model. Finally, we'll go through that tuple of tuples that we had set up earlier to look at 5 different images. We'll use Pillow to load that image. We'll ask the model to make a prediction on that image, and then we'll render that image to our screen, either with both the ground truth in blue and the prediction in green. Let's run these cells. All right, so let's look at what the model predicted. For the first one, it's clearly an F16, and that's both the ground truth and the prediction. Scrolling down, we see that the model accurately made predictions on a Lockheed L1011, a McDonnell Douglas DC-10, a Cessna 172, and a Eurofighter. Now, in machine learning, a model is never going to be 100% accurate, and that's an important part of building an application, is to set expectations to the user and figure out ways to manage the inevitable inaccuracies from the model. Looking deeper into the output of our model, we can actually see that the model was 65% confident on the F16. That's really not too bad given that there are 10 classes. But for the second image, it was only 44% confident that it was an L1011. You can see that there was quite a bit of confusion as to whether the image was a McDonnell Douglas DC-10 or in this case label 5, which is a 747. Probably because of the passenger livery. It's super confident that the final image is a Eurofighter, which makes sense given the very distinct look of that jet. And that wraps up the demo. In this video, we've talked about what Masterful is, namely a low-code platform to train computer vision models, as well as why you'd want to use it, namely a much simpler interface and much more powerful algorithms than a lot of the alternatives out there. We also went through a full demo of training a model with the platform. If you'd like to learn more, come to our website, www.masterfulai.com, or join our Slack community, or email us at learn@masterfulai.com. Thanks.